Some homeworks? Nolan, we'll start with you. You got your hand up first anyways. 86.
I was just wondering, I think I got it, but I was a little confused when...
Oh, yeah, with the 0 in there? Yeah, we'll draw it. That's a good one. That's big. All right. Let's see here. Add shape. Okay. So remember that this is like X, Y, Z. So 3 in the X direction, 1, 2, 3. 0 in the Y direction. So when I initially draw my parallelogram, there is no parallelogram. It's just a straight line. So I only have 2 points to project into the Z direction instead of 4. Then we're just going to project up 2 units in the Z direction. So like 1, 2. Project up 1, 2. So like that's my new point. So if I draw my vector, then that's it. Yes, sir.
Does the x-axis go like that or like that? Yeah. I don't know.
Oh, did I draw that negative?
Like the x-axis is like going the opposite direction in general. The bottom left, top right.
Right, you meant oh. You wanted to go here? Yeah, whatever.
So it doesn't matter which way it goes?
I mean, it's just a matter of perspective. If you imagine like it coming out, it's still the same thing. Like it's coming out of the board. So like however you want to think about it, the X is like coming straight out from you, you know. So it's like 6 of one, half dozen the other. Whether you think about it coming from like, it's just like it's a perspective thing. You know what I mean? So it's, I don't know. I don't think it matters. It's short of my answer. Is that okay?
Yeah. Thank you.
Okay, cool. Others, I heard lots of people shuffling their stuff around when I volunteer or was opening for questions. Morgan.
Did you do like 68 and 69?
I sure hope I can. Be kind of embarrassing if I couldn't. Okay. All right. Boy, that's huge in there, huh? Whatever. Okay. So it says find the slope-intercept form for the following lines given as vectors. So what I'm going to do is I'm going to convert this from linear combination form, which is how it's written, into that standard IB component form. And then from there, take it into slope-intercept form. And then I'll show you how to go directly after we do that. So what I remember is that the I vector is like the x components. So I have an x component without a t and then an x component with a t. Okay with that, Morgan?
Yeah.
And then the same thing here. I have a y component without a t and a y component with a t. So that's my IB component form. from there, I can note that the slope here is going to be y over x in the slope vector. And the point we have is the point 1, -2. So if I want to write this as a Cartesian equation, I can do y minus y1 equals m times x minus x1. And then if I simplify this down, I have positive 3/2 plus, and then I subtract 2 from both sides to give me -1/2. And so there we go. Alternatively, I can say, okay, my slope is going to be the t coefficient from j over the t coefficient from I. So like, right? And then my point is going to be the x coefficient from, or the constant from the I vector and the constant from the j vector. So you could take it that way also, without having to rewrite it in the IB component form. But like, that's essentially what we're doing. Is that cool? Okay. And then 69, it says to find a possible vector line equation IB component form for line that intersects the following points. So why does it say possible there? Yeah, there's infinitely many possibilities. So my vector line equation needs to look like this, right? What are my values that I can pick for R? Or R naught, excuse me? The two obvious choices would be the 2 points that are given, just vectorized, right? Are there other R naught possibilities? Yeah, but you'd have to find them, and like, who has time for that? Not me. For our vector V, we have two choices. Basically, we have head minus tail, where I treat the first one as a head and the second one as the tail, or the reverse. So any combination of those two pairs of vectors would be fine. I'm just going to take the first set from each. Again, are there other vectors other than these four that I could use? Yeah. Would they require a lot more work to get to? Or unnecessary work to get to? Yeah. Why would you do that? I don't know, you're crazy, right? Just use one of these four, right? One of the point vectors, one of the direction vectors. The nice part about the direction vectors, it doesn't matter like which point you call the head and which one you call the tail. It doesn't matter. You just do x minus x, y minus y, as long as you keep the pairs of points. You know, whatever you pick to do first for x, you have to do first for y. It doesn't really matter, which is lovely, right? It's like, I love it when it's just like, just do some stuff. It doesn't really matter. Allie.
Can you go over one example for the set 55 through 58 and 59 through 62? Like just one from each.
So these two?
Yeah.
Sure. I guess I should be like, oh, I did circle those. Okay. Great. You just want me to do like 55?
Yeah, I don't care which one.
Okay. So all we're doing here is I am going to plug the vector 5, 2 in for R and see if I can solve that for T.
Okay.
So all that means is I'm going to set up two equations, one where the X component is equal to 5 and one where the Y component is equal to 2.
Okay.
So I'm just going to solve each of these separately for T. So I'll add 3 to both sides, giving me 8, and then divide by -2, that gives me -4. Here I'm going to subtract 14 from both sides, giving me -12. Divide both sides by 3, giving me -4. Since these are the same, we'd say yes, the point 5, 2 lies on R. So that's all we're doing there.
Yeah.
Is that cool?
Yeah, that makes sense.
Okay. And then you said one of these. Okay. So just do 59 maybe. So here I'm going to say, okay, well, I have the slope 2. So that's the vector 1, 2. And I have the point 0, -1. So that's going to be the vector 0, -1. That's everything I need to write my vector line equation. So I have point vector plus slope vector times T.
Oh, okay.
Pretty easy. And in general, like you're noticing most of the problems from this chapter are really easy. It's just a question of like vocab. Do I understand? Like, what is this asking me for? And then like, even if I understand the vocab, what's going on, like, and the notation, it's just like a lot of the things are kind of feel similar, right? Like the way I do this is really similar to the way I do that. And like keeping everything straight can become kind of a hassle. But like in general, the techniques here are pretty straightforward, right? There's nothing that's taking like, well, that was like 15 lines of, you know, algebra to get to, which is usually like a little bit algebra, but not a lot. But you got to know the definitions, you know, like what is this asking me for? And that's really the hard part. That's the part that takes just some time. As opposed to Mr. Kulik makes it easy because he's been doing this for, you know, 15 years or whatever. So like the vocabulary he has down pretty pat. That's why it looks easy when your math teacher does it. Because they've been doing it for a long time. Imagine how good you'd be at this class if you had to do it every year for 10 years. Like the same class, just 10 years in a row. You'd be really good. You'd be really, really good at it. Anybody else? Cool. All right, well, let's finish this chapter up. Let's see. So 8.8. What did we call this section? It's something line versus line. It's like interactions or something. Blah, 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 blah. Intersections line, 3D intersections line, first line. Okay. Okay. So you have two lines in three-dimensional space. 4 things can happen. 3 of them should be obvious because they're the same things that can happen in 2 dimensions. That would be, for example, what? Okay, intersect how many times? Okay. Okay, what else can happen? Okay, intersect infinitely many times, aka they're the same line or they coincide. Okay, what else could happen? So they're parallel, and I'm going to add in non-intersecting because technically the coinciding lines are also parallel, right? They have the same slope anyways, the same direction. And what's the fourth outcome now? What can happen in 3 dimensions that couldn't happen in 2 dimensions?
So it can just be like next to each other, kind of, but not parallel. But...
Yeah, you can have non-parallel, non-intersecting. And Nolan, that's exactly the right picture. Imagine you have like 2 planes that are parallel. One line goes like this way, and the other line goes that way. Those are clearly not parallel because you can't find like a third plane that contains both lines. But they're also not intersecting, right? Because they're contained in parallel planes. Yep, that's dead on. So we have non-parallel, non-intersecting. I'm just going to abbreviate that situation as NPNI because that's a lot of letters to write. Everybody's okay with this? I'm going to make a flow chart to help us kind of figure out what's going on. So the goal in this section, let me backtrack just a second. The goal in this section is I'm going to give you 2 lines, and I want to tell you what's going on, right? So I want you to be able to tell me, okay, are they intersecting? And then give me the intersection. Are they coinciding? Are they parallel but non-intersecting? Are they non-parallel, non-intersecting? Right? I want you to be able to give me which of those 4 situations is going on. So we're going to build a flow chart to kind of help us work through a process, be able to figure out what's going on here. So the flow chart we're going to build is basically the same as the 2-dimensional flow chart we built. Just we have an extra branch because we have 4 possible outcomes instead of 3. Everybody's okay with that? All right. So let's say we have some vector R1 with point vector R1, 0, direction vector V1 times, I better use alphabetical order, I'm going to get confused, S. And my other line is R2 with point vector R02, direction vector V2, and parameter T. And we're trying to figure out, like, what's going on? What are these 2 lines doing? So the first question that we're going to ask is, do these lines have the same direction? How do we check that? We want to check to see if V1 can be just some scalar multiple of V2. So if the answer is yes, they have the same direction, what are the 2 possible outcomes there? Good. Exactly right. They'd be coinciding or parallel. So if they do not have the same direction, then they must be either intersecting or NPNI. Everybody's cool with the first split? Same first test we did for 2-dimensional, right? Same test, same technique. That's wonderful. I love that. Okay, to tell the difference between parallel and coinciding, we want to ask, is the point vector from the first equation on the line for the second equation? And it doesn't matter, I guess, if you take the point vector from the first equation and plug it into the second equation, or you take the point vector from the second equation, plug it into the first equation, right? Same process, doesn't matter. Everybody's good? Okay. If we get yes, the point vector from the first equation is on the second equation, what does that mean? Good, they're the same line. This is coinciding. And if not, then we have the regular parallel situation. Okay. So to check the difference between intersecting and NP-NI, we want to check to see if these two have an intersection. To do that, we just set the two equal to each other. We form our system of two equations, or our system of three equations it'll be, because we have x, y, and z now. We solve that system for s and t. If that system has a solution, that tells me they're intersecting. And we can plug the parameter for s or t into either R1 or R2, depending on what you're using, s or t. If that system doesn't have a solution, then we have like an NP-NI situation. Everybody feel okay with this kind of flow chart, it kind of explaining what we're doing? This is one you'll want to be familiar with for the test, right? Because you'll have to do this process on the test. The nice part is it's basically the same process as the two-dimensional process. And most of these skills, these tests that we're doing, are the same thing as like the other kinds of problems we saw along the way. So that's really nice. Because it hopefully makes it pretty easy to remember. All right, let's grab a couple of these, do these couple of example problems, and we'll be donezos. All right. All right, so we have determine the relationship between the following pairs of lines. If there's a point of intersection, solve for it. So the first thing we check for is the direction. To do that, I take the direction vector from one of them and see if it's a scalar multiplication or scalar multiple of the direction vector for the other. Now this one's pretty easy, right? You should be able to look at this and tell what's going on. What do you guys see? Yeah, so k equals -4 would make the two vectors the same, right? What does that tell you?
Yes.
Yeah, they have the same direction. If you can't do that in your head, that's okay. just look at them one at a time, like 4 equals negative 1k, solve for k. Negative 12 equals 3k, solve for k. And just do it one at a time. You should get the same value for k for all of them. Otherwise, they're not the same direction. Even if one of them is different and two of them are the same. Everybody's cool with this? So what does this tell me then?
You have to check, see if they're the same line.
Yeah, so we know they're parallel or coinciding, exactly right. So the next check is, does R01 lie on R2, for example? So that's 233 equals 307 plus negative 1, 3, negative 4. What was the variable there? S. Okay. So we'll solve the first equation. 2 equals 3 plus negative s. So I get s is 1, right? And then 3 equals 0 plus 3s. So s is 1. And then 3 equals 7 plus negative 4s. I get s is 1. So what does this say? That the point from the first line lies on the second line, and if one point is the same and they have the same direction, all their points are the same, we're coinciding. This is the easiest side to do, right? The check over here is much shorter than the check on the intersecting non-parallel, non-intersecting side. But that's okay. Still an okay. Pretty easy, right? I like it when it's easy. Happy so far? Again, this is as bad as it gets are these problems. These are the most involved thing that we're asking you to do in this chapter. So that was easy. Look at how much space I took to do this in the explanation. It's just hard to draw that map that we drew in there at the beginning, like the flow chart inside the lesson. So it takes a lot of words. All right, another example. Same directions. So we start the same way. So let's see. This one, not so obvious that I can do in my head. I have 4 equals negative 6k. If I divide by negative 6, I get negative 2/3. Then I have 5 equals negative 9k. I divide by negative 9, I get k equals negative 5/9. And right there, I'm stopping. Right? Because I know those aren't the same. And doesn't matter what the third one is. If I get 2 that disagree, why would I do extra work? I know what's happening. They ain't the same direction. And you could probably see that by inspection anyways, right? If the first one is 2/3, obviously 4 isn't 2/3 of 9, right? Or I'm sorry, 5 isn't 2/3 of negative 9. Anyways, whatever. Next, so that tells me this is either intersecting or NP/NI. So we check to see if we can solve for R1 equals R2. So I've got this. Now I'm going to translate this into a system of equations. So 2 plus 4t equals negative 2 minus 6s. 4 plus 5t equals negative 4 minus 9s. 1 minus 3t equals negative 1 plus 2s. At this point, something is occurring to me. And it's that if you are a bad penmanship person, I might have changed the letters for my parameters from S and T that look a lot like a plus sign and a 5 into something that I know I can't screw up and confuse with some other symbol like A's and B's or something. So word of advice for you bad penmanship people, be cautious about that, or change your names of your letters there so that you can't confuse yourself. I'm going to just be extra careful because at this point I'm pot committed to S's and T's, but I'm already wary because those S's look an awful lot like my 5s. All right. Now I'm going to get this in a format where I can solve this system with my calculator. So I'm going to add 6s over to the left side and subtract 2 over to the right side. And then do the same thing with the second equation and the third equation. Now I'm going to solve that system with my calculator. What do you notice, though, that's kind of weird about that system? How many variables do I have? 2. How many equations do I have? Is that a problem? Okay. So how many equations do I need to solve a system with 2 variables? 2. Does it matter which 2 I choose? No. Does the third one matter? Yes. It still does matter. I'll show you why in a moment. We'll talk about it in just a second. Kind of is the answer to that. So I'll go into the matrix menu, go to the edit tab, type in my matrix. So this is still a 2 by 3. So I have 6, 4, negative 4, 9, 5, negative 8. Notice again, I'm using only 2 of the 3 equations. I'm not using all 3. If you use all 3, you'll get a line of all zeros at the bottom if it's solvable, and that'll be confusing to you because that usually means infinitely many solutions. I'll go back to the matrix menu this time and then grab from the math tab the RREF command. Do that on matrix A. I press enter and I get S is negative 2 and T is positive 2. Does that mean the system had a solution? Not yet. It means that the first 2 equations in my system had a solution. I still need to check if this solution satisfies the third equation in my system. It is possible for the first 2 equations to have a solution that fails to solve the third equation. If it fails to solve the third equation, this is non-parallel, non-intersecting, because the system of 3 equations has no solution. And that can happen. So -2 for S and +2 for T do satisfy the third equation as well. So this system has a solution. These two lines intersect. How do I find their point of intersection? Like that was going to do anything. All right. How do I find the point of intersection then? Because the point is a three-dimensional point, right? So -2, 2 is not clearly my answer. Yeah, I plug either -2 in for the S in R1, or I plug +2 in for the T in R2, or vice versa. I can't remember with which one had the S on it, which one had the T on it. R1 had the T this time. So 2, 4, 1 plus 4, 5, -3. And then my value for T is 2. I picked the T. Why? There's no negative sign on it. Just makes it like a little easier. So my point is going to be 2 plus 4 times 2. So that's 10. Comma 4 plus 5 times 2. That's 14. And then 1 plus -3 times 2, that's -5. So there's my point of intersection. And again, you could have used R2 and -2. That would be fine. I'll give you the same point. And if you really want to make sure, you could do that as a substitute for this check here to conclude they're intersecting. That would be satisfactory as well if you want to check both that S and T give you the same point for R1 and R2. You could do it that way as well. That would be okay. Does that feel okay, guys? So again, the place where we're looking to tell the difference between like the non-parallel, non-intersecting is this system. This system will fail to have two solutions in two different ways, right? The matrix could come out where you have like, you know, a row of zeros with like a 1 here. That would tell you it's no solution, where you have like 0 equals 1. Or if you get a solution to your system and it fails to check on the third equation, that would also mean there is no solution. Either of those outcomes tells us NP-NI. What do you guys think? Just takes a little bit of practice. It's not so bad. It's a lengthy-ish, but you know, it's not like I took all the space in the world to do this, right? You know. All right. At this point, you guys should be able to do the rest of the problem set, 119 through 122. Yeah.
Would there ever be a situation where if you plug like the variables into like the third equation, where like the points won't match? Like if you did both of them, would there ever be a situation where they wouldn't match?
Yeah. Yeah.
Well,
so
if that happened, would it just be NP-NI?
So if I plug these two into 3 and it doesn't work, that can happen. That is NP-NI. Yes. And that can happen. All that's saying is that like in 2 dimensions, if you had like projected the lines down into 2-dimensional system, they would intersect. But when you project them back out into 3 dimensions, now they're like in 2 parallel planes. That's kind of what's happening there. Is like in the X and Y component, they would intersect, but there's a Z component, and if they're now parallel in the Z, they'll be NP-NI. That's kind of what it's saying. Does that visually make a little bit of sense as to like how that would happen?
Kind of.
Kind of. And that's good enough, right? We're not being like 3D geometrists in here. I'm just trying to give you like some intuition as to like why that's a reasonable thing that could happen. All right. So I think now for what Sunday is the 12th, right? And we're like, are we 89 to 118 was what we had before? Is that right? Maybe. No?
No, last or
Yeah, 89 to 118 was for this Sunday from before.
no, it was 88.
88 was this Sunday, I thought.
Yeah, it was due yesterday.
Yeah, it was due yesterday. Next Sunday, we had already assigned 89 to 118.
Yeah, I thought you meant that was.
That's okay. I just wanted to make sure we're all on the same page, that I was on the same page, that you guys were on the same page. We're code pager. Get it? Because I was saying code planer, but we turned the plane into a page. Anyways, so that's for this Sunday. Sounds like many, based on your questions, many of you have already gotten past 89, right? Which is great news. Those last 4 questions are the most involved questions in the thing, but they're just like the examples we did. Like they're not bonkers or anything. In fact, they're probably less time consuming than the story problems were, right? So next class we'll do the review day. The plan was to do the test Friday. I heard that Friday is a particularly bad test day for most of us. So we'll just start chapter 9 on Friday and we'll do the test on the following class day, Wednesday. Or Tuesday, excuse me. Everybody's cool with that? You're welcome. In general, Mr. Kulik doesn't care what the test day is. So when that kind of thing happens, if you let me know, we'll just start the next stuff and take the test when it's more convenient or less inconvenient anyways. We're just looking for not a terrible Thursday for everyone. You know what I mean? Thursday night anyways, right? So yeah, you guys feel okay? We got what, like 30 or so minutes left here? Maybe a little bit more. Get your stuff out. Knock some of this problem set out. Try some of these last 4 problems right now while the process is fresh in your head. Cement it in there. Do some on your own. Or with your friend, you know. You can compare some answers, talk through what you're doing. Make sure you got it. Okie dokie.